So thanks for coming to this afternoon session. And we'll start right now with Anand Natarajan from MIT, and he will talk about robust self-testing of multi-qubit states.
Okay, can everyone hear me? Okay, so thanks for the introduction. So this is joint work with Toma Vidic from Caltech, and so I'll just get right into it. So first of all, I'll start with the definition of what self-testing is. So the basic question that we try to answer here is if someone gives me a box with some unknown quantum state inside, how do I tell what the state is? So there's maybe another setting in which you would have heard this question, which is the setting of tomography, in which I have the state, but I also have a measurement apparatus over which I have full control. And then by measuring the state and looking at the outcome, I can deduce what the wave function of the state was. So that's tomography. Self-testing is something else. We want to assume this. We want to get rid of this assumption that the measurement device is known. So instead, we're going to just ask whether we can characterize some global property of the state, like the amount of entanglement in the state, using only the assumptions that quantum mechanics holds and some sort of causality assumption. So the way we do that is we assume that the state is split between two entangled provers. We call them Alice and Bob. And then there's a verifier which sends questions to the provers and gets back answers. And under the assumption that the provers cannot communicate, we can sort of deduce from their answers whether they share a particular state or not. And just for the, in case you've seen these words, so this is very closely related to the notion of a non-local game or a one-round MIP star proof. I'll say a little bit about that later, but for now, just these things are all essentially the same as self-testing. So a bit more quantitatively, we say that we can test a state psi up to error epsilon if we have a test with the following properties. So the test needs to have completeness, meaning that the state psi should be able to pass it. So the probability that the verifier accepts psi should be at least C. So C is called the completeness parameter of the test. And then the test should be sound, meaning that no state that is far from psi should be accepted with high probability. And so the way we phrase that is that if any state phi is accepted with probability at least S, then phi had to be pretty close to psi all along, meaning there exists some local isometries U and V such that U tensor V acting on phi will get me close to psi. And I need these isometries here because I have I can never hope to test anything better than that. There's always this freedom of applying local isometries that either party could apply. So when I talk about the robustness of a self-test, what I mean is the difference between these completeness and soundness parameters, this gap C minus S. So experimentalists often talk about stronger notions of robustness, but that's what robust means in the context of this talk. OK, so what's an example of something I can test? It turns out you can test a single EPR pair using the CHSH game. So I'm sure you've heard of the CHSH game. This is a game that can be won with probability 3/4 with classical players, but using a shared entangled state consisting of one EPR pair, you can win it with probability 85%. And so the self-testing result for this game says that if you win it with probability that's close to optimal, so here, if you win with probability that's like 85% minus epsilon squared, then your state must be close to one EPR pair. And this result was given by McCaig and collaborators. But this idea has been around for a while, that you can use these games to test for EPR pairs. So that's testing a single EPR pair. What I want to test a lot of them. So there's been a lot of work on this question, which I've summarized in this table here. And sort of the point that's important is that all of these previous works for n EPR pairs, they have a completeness-soundness gap or robustness that shrinks with n. So in most cases, it's inverse polynomial in the number of EPR pairs n. So a natural question you might ask is this necessary? Can I actually test for n EPR pairs with a gap that does not shrink in n? And that brings us to our first result, which is to say, yes, you can. So we show a two-prover self-test for n EPR pairs with questions that are n bits long and answers that are a constant number of bits long. And if you want to test the n EPR pair state up to error epsilon, then the completeness-soundness gap you need is epsilon to some constant. It's some terrible constant, 1 over 32, but it doesn't depend on n. So in this sense, we say that this test is robust. And also, another nice feature is that the completeness we achieve is 1. So if you do have any EPR pairs, you'll pass the test with certainty. So that's the sort of the main result. And our second result is really an application of this, which is we give a test for ground states of local Hamiltonians. So the way we phrase this is, if you recall, the local Hamiltonian problem is given a Hamiltonian on n qubits, determine whether the minimum energy is below A or greater than B, where A and B are separated by an inverse polynomial in n. And so our result is that we have a 7-prover, 1-round MIP star protocol, so like a 7-prover test for the local Hamiltonian problem with essentially the same parameters as on the previous slide. So n-bit questions, 1-bit answers, and a completeness-soundness gap that is a constant independent of n. I just want to point out at this point that you could get a protocol with similar parameters by following this chain of inclusions that QMA is contained in NX, which is contained in MIP star. But the protocol you get that way is considerably more complex than the one we have here. And also, our protocol has the nice feature that the honest provers do not need to be very powerful. So they only need the power of BQP plus access to the ground state that they're trying to prove to you that they possess. Whereas if you follow this chain of inclusions, you need the full power of NX. OK, and now here's a second application, is to delegated computation. So the setting of delegated computation is I have a verifier that's classical, and it wants the provers to do some quantum computation and confirm and verify that they have actually done the correct computation. So our result is that we have a 7-prover, 1-round protocol for any computation in BQP, where the questions you ask will be basically O of n, where n is the size of the circuit in BQP you wanted to compute, and 1-bit answers, and again, a constant completeness-soundness gap. So this is actually almost a direct consequence of the previous result, just by taking your computation and encoding it in a history state, following the idea of Kitaev. So that's those are our main results. And so I'm going to now talk a bit about the techniques, and towards the end, I'll come back to maybe implications of these results for the quantum PCP conjecture or other things. But let's get into the proof techniques. So how do we prove that, how do we achieve a test for an n-qubit state, and how do we analyze it? Well, the main guiding philosophy for us was that if you want to test an n-qubit state, you need to test n-qubit observables. So you need the honest strategy of the provers to involve measuring sort of all the qubits at once in some way. So a lot of the previous work had involved only measuring a few qubits at a time, or like sequentially measuring one qubit after the other. And this seemed to lead to losses in the robustness. So what we consider is strategies where the honest provers would have to measure the n-qubit Pauli operators, which we denote x sub a and z sub b. So x sub a means that for a string a in 0, 1 to the n, I measure the Pauli x on all those locations where a is 1, and then I take the product of all my answers. So that defines some big global observable. And likewise, z of b is I do the same thing, but with z. And then how do I test that the provers are actually applying these observables? Well, I test that they satisfy the correct algebraic relations. So meaning that the products of them behave as they should. So there are two types of relations that these Pauli observables satisfy. One is what we call linearity. So if I take x of a times x of b for any a and b, that's exactly equal to x of a XOR b, where the XOR is taken bitwise. Another property is anticommutation. So as you know, the Pauli x and Pauli z operators anti-commute with each other. And so if I have multi-qubit Paulis, that's just saying that the phase I get when I exchange them is -1 to the inner product mod 2 of a and b. So these are the two types of relations that we'd want to test. And then we hope that we can use that to deduce that we have n-qubit Paulis, and therefore we have the state that we want. So putting that philosophy into practice, here's what our test looks like. It's essentially the things I mentioned. So there's a test that looks only at the Pauli X operators and checks that they satisfy this linearity relation. There's another test that looks at the Pauli Z operators and checks that they satisfy this linearity relation. There's an anticommutation test that measures this phase that I'm supposed to get when I commute them. And then finally, there's a consistency test that just makes sure that both players give me the same answer when I ask them the same question. This is just useful in the analysis. So now let me sort of state a bit more precisely why this test is correct. And this is really formalizing the ideas that I had 2 slides ago. So the main theorem we want to show, remember, is that success in this test implies that the provers share n EPR pairs. And so we break up the proof of that theorem into 2 steps. First, we prove this lemma, which is actually all the hard work, which is that success in the test implies that there exist operators, which I denoted x prime of A and z prime of B, that exactly satisfy the Pauli group relations. And then I claim that once you have those, it's quite easy to obtain the state. How do you do that? Well, any set of operators that exactly satisfy these relations is sort of isometric to the Pauli group. So there's an isometry mapping the Hilbert space they act on to C2 to the n, and that maps these x prime and z prime to the true Pauli operators sigma x and sigma z. And then you can basically use the fact that the EPR pair state is characterized by its stabilizers. So if the state is stabilized by x, x, and z, z, it must be an EPR state. So that's why having Pauli operators will give you the state. So now we've reduced the problem to just testing for these Pauli operators. So now I'm going to go into how those individual subtests work. If you recall, there were 2 tests. There was a linearity test and an anticommutation test. So I'll start with the linearity test. Now this is based on some old classical work in a field called property testing of functions. And it turns out there's an analog of linearity that makes sense there, and there's a test which we can easily quantize. So let me tell you about the classical test. So in the classical setting, instead of observables, we just consider Boolean functions. So say I have a function that maps from 0, 1 to the n to 0 or 1. And I say that this function is linear if for all points a and b in 0, 1 to the n, f of a XOR f of b is equal to f of a XOR b. So an example of such a function is if I take some fixed n-bit thing, some fixed point in the Boolean hypercube, and take its inner product mod 2 with the argument x. So there's this classic theorem due to Blum, Luby, and Rubinfeld that says that this property that f is linear can be checked by a test. And so the way this theorem is phrased is that if I pick a random point A and a random point B independently and uniformly at random, and if I check that f of A XOR f of B is equal to f of A XOR B, and if this check passes with probability at least 1 minus epsilon, then there is some perfectly linear function g, which is quite close to f. So it agrees with f on order epsilon fraction of the coordinates. And so the way I've written this thing here, it may not look quite like the self-test I was talking about, but you can, in fact, evaluate that probability through a self-test. So you can, it's this test here where the verifier basically queries Alice and Bob for the value of the function on these points a, b, and a plus b, and then verifies that it satisfies a linearity relation. So the theorem I wrote on the previous slide says that if this classical self-test passes with probability 1 minus epsilon, then the shared function that Alice and Bob have is close to being exactly linear. So that's the classical picture. What happens when we go to the quantum world? Well, it turns out that almost the same test works, and in fact, you can even use almost the same proof to prove that it works. So I'll state here the theorem. So if I have a collection of observables, capital X, such that when I check it at these random points, a, b, and a plus b, it's close to satisfying this linearity relation, then there's some other collection of observables y that is exactly linear and is close to x in its action on the state psi. So that's the quantum linearity test. And as I said, the proof is actually quite similar to the classical linearity test. OK. So that's how the linearity test will give us these collections of observables x sub a and z sub b that satisfy the linearity relation. How do we check the phase relations between them? This, it turns out, we can do using some ideas from the single qubit self-test. So if you recall the single qubit CHSH game, the proof that this is a self-test involves showing that it certifies that there's an x and a z operator on the prover space that anticommute. And now it turns out that if I have any pair of anticommuting operators, I can think of them as a qubit. So here I've drawn 4 physical qubits. And so x acting on the first qubit and z acting on the first qubit gives me an anticommuting pair. So I can call that one qubit. But also I could have considered the Pauli operator acting on the first 3 qubits in the x basis and one acting on the last 2 in the z basis. So these also anticommute, and so they behave algebraically like operators on one qubit. So that means that I can test for them using the same test I used for a single EPR pair. So I can take the CHSH test, and I can just play it on this pair of operators and check that if I pass with high probability, then that implies that these two are close to anticommuting. And so the way we use this is then we just pick at random an A and a B that form an anticommuting pair in the set of n-qubit Pauli observables and run the CHSH test. And that tells us that most of these pairs are close to anticommuting. And I just want to say there's nothing special about CHSH here. This whole analysis works with any game that certifies anticommutation. So for instance, it also works with the magic square game or any other game you could come up with. OK, so now just to recap what I've said, so I presented this test that had 3 components, right? It had a linearity test in the x basis, a linearity test in the z basis, and an anticommutation test. And basically, I showed you why each of those tests individually will certify that the property being tested actually holds. And then it turns out that when you have all these properties, you have essentially the entire n-qubit Pauli group, and that implies that you have n EPR pairs. So this is the proof of our main theorem in outline. So now I want to say a few words about how we go from EPR pairs to ground states. So this is actually following a long line of previous work, which started, I guess, from this paper of Fitzsimmons and Vidic in 2014, which was in QIP 2 years ago. And then there was a paper by Zhengfang Ji in last year's QIP. And we follow a similar approach to both of these. And the idea is that if I have a ground state of a local Hamiltonian, the way I can test it is I can first take each qubit of this ground state and encode it with an error-correcting code, and then split up that encoded state amongst the provers that I have by giving each prover 1 qubit of the encoded state. So here, if I've drawn an illustration of how this works with the 7-qubit code. So I started with the state psi. Then I encoded it. So each qubit in the original state became 7 qubits in the encoded state. And then I gave one of those 7 qubits to each of these 7 provers. And now it turns out that you can sort of that checking that these 7 provers share an encoding of a state is mathematically quite similar to checking that they share an EPR pair if I divide them up between one prover and the other 6. So that's essentially how our test works. We first pick at random one of the 7 provers to play as our Alice. another, and then we take the rest of the 6 and call them Bob, and we play a version of the EPR pair test. And then finally, we have another test which checks that the state, in fact, has a low energy. So that's an illustration of how to go from testing EPR pairs to ground states. And again, this idea is basically based on these previous works. The main new component here is our new test for EPR pairs. OK, so now I want to sort of conclude with some discussion of implications of this result for the quantum PCP theorem. So let me first of all say, why does this have anything to do with the quantum PCP theorem? So if you haven't heard of it, the quantum PCP theorem is, well, I shouldn't call it a theorem. It's actually a conjecture that people have not proved yet. And it basically concerns the computational hardness of these proof systems that involve multiple interactive provers that share entanglement. So that's the proof system MIP star. And you can think about that as the proof system that corresponds to these self-tests. So if there's a computational problem such that I can self-test answers to that problem, that's something that's in the class MIP star. So the conjecture that's called the MIP star version of quantum PCP is that the class QMA should be contained in MIP star with a small question size, so log n bits of communication, and also a constant gap between the completeness and soundness. And so this thing is analogous to a theorem in classical complexity theory called the PCP theorem, which says that the class NP can be checked by multiple prover interactive proofs with the same parameters, except no shared entanglement. So there's been work in progress towards proving this conjecture. So this work of Fitzsimmons and Vidic showed first that QMA is contained in the class QMIP, that is, interactive proofs where I'm allowed to send quantum messages with log n size messages and an inverse polynomial completeness-soundness gap. And then subsequent to that, the work of Zhengfeng Ji showed that I could replace the quantum messages with classical messages. However, these proofs remained non-robust. So the completeness-soundness gap was still inverse polynomial in the number of qubits. So how does this work fit into that? Well, what we do is we obtain this constant completeness-soundness gap, but at the cost of blowing up the communication. So now we have an MIP star protocol with n on order of n bits of communication, but the completeness-soundness gap is a constant. And so if you want to relate this to classical results, this is similar to a result that's called the toy PCP in the classical world, which said that NP had proofs with n bits of communication and constant completeness-soundness gap. And in fact, the proof of our quantum result draws on ideas from the proof of this toy PCP. So in terms of future work, to prove this MIP quantum PCP conjecture, what we'd have to do is, if we could reduce the size of the messages in this proof system while maintaining the robustness, that would essentially give us the quantum PCP conjecture. So one interesting idea is that we are excited about is that this work was able to draw inspiration from this classical work on property testing of linear functions. And there was similarly classical work on testing low-degree polynomials that was very important in the proof of the classical PCP theorem. So we hope that maybe more ideas from there can be used to attack this quantum version of PCP. Now, there are also other applications that we believe should exist for this kind of self-test. One of them is device-independent quantum key distribution. So a lot of quantum key distribution protocols involve the two parties that are trying to communicate having to share EPR pairs and then measuring the EPR pairs to obtain some key. And so it seems plausible that an improved test for EPR pairs will let you give better key distribution protocols. Another possible area of further research is blind delegated computation. So if you recall the delegated computation protocol I presented earlier was not blind in the sense that the provers had to know which computation they're supposed to be proving to you. Whereas in a blind protocol, the provers don't know which computation they're trying to execute. So that's something that would be interesting to look at. And yet another possible application is that the classical linearity tests that we drew on in the proof of our result were used also as a form of alphabet reduction for classical probabilistically checkable proofs. And so we're wondering if this could be used as a form of alphabet reduction for quantum games. So if we have a quantum game where the answers come from some very large alphabet, we replace that by another game where the answers come from a small alphabet by composing with this self-test. And then finally, one open question that I guess we had thought about when we were completing this work, and then we realized it had been solved, was applying this test of EPR pairs to dequantizing general interactive proofs. So taking any proof in the class QMIP and putting it in the class MIP star. And then this recent work of Zhengfeng Ji, which was presented on Monday, actually achieved this result. But it would be interesting to see whether our self-test for EPR pairs could be used to strengthen the results achieved there. So in conclusion, that's everything I had. So I'd be happy to take questions.
Yeah, questions?
Thank you. In DIQKD,
yeah.
Many Bell tests failed because in experiments the detector efficiency is very low.
Yeah.
So such as CHSH inequality it failed. So do you think your self-test can decrease the requirement of detector efficiency? Thank you.
I think it does address that in some sense, in that, like, for instance, I believe so there's earlier self-tests for, like, many EPR pairs that are based on, like, iteratively playing the CHSH game, and there, because the completeness-soundness gap was inverse polynomial, you sort of, I guess if you mess up a few rounds of the game, then you lose all the power you had, and so I expect that this will help with that. Yeah. However, I should say there's another notion of robustness which we don't address, which is that in the implementation of the honest provers, like when the honest provers are performing their strategy, they need to, like, if there's some error in their apparatus, then that could cause them to fail the test, right? So that's a notion of robustness which we don't address and is something that's interesting for future work.
So you said that your constant soundness gap increased from the previous work.
Yeah.
But your number of questions went to n. Mm-hmm. So is it because of the EPR self-test? Like, how did it help exactly?
Yeah. So this comes back to our philosophy of like testing n-qubit observables to get an n-qubit state. So like in many of the previous works, the size of the questions could be small because in the tests, you're only asking the provers to measure, say, 2 or 3 qubits at a time. So the questions you ask are just like the index of the qubits you need to measure. Whereas here, we're asking them to measure these big n-qubit Paulis that touch all of the qubits. So we need to really send them n bits of information in the questions. So that's how I would understand the trade-off that's going on there.
OK, so if there are no more questions, let's thank Anand again.